Good morning, everyone. Welcome to day 4 of our 2021 Pacific Northwest Pretreatment Workshop. I'm going to go over a little bit of housekeeping items, and then I will go through our agenda and then introduce our first speaker. So as you recall, day 4 now, for those that need CEUs, please participate in the polls at the end of each session. And you will earn 0.1 CEUs, and certificates will be sent to you at the end of our workshop as committee members gather all that information together and then distribute it to you. There is a Q&A box, so please utilize that for presentation questions. And we can be able to help you out and get those answered. And if you have any technical difficulties, please use that as well. And just to be aware, this is different than the chat box. Please use the questions labeled box. We will have a break after every session for 5 minutes, and we'll try to gauge that and make sure everybody's able to grab coffee or use the restroom and continue on. We will value your feedback at the end. Some folks have been confused in expecting a survey after each day, and it's actually at the end. So after our final day on Tuesday, November 16th, there'll be a survey regarding the whole workshop. So if you have any specific notes regarding certain speakers or anything, perhaps take notes on those, and then you can remember them for our survey. We would greatly appreciate it. And the presentation will be recorded, so please note that if you need to follow up in the future. We'll have it distributed on pprc.org website, and Ken will be loading that up in future weeks for us. The agenda today, I don't know if folks tuned in yesterday, will note that we had a bit of changes with a couple of our speakers. So today's agenda will have industrial wastewater monitoring with Ken Navidi, and then local limits submittal package with Dave Knight, ethics and accountability and inspection and monitoring for pretreatment inspectors and managers with Angela Walker, and then digitizing POTWs and water providers, advancing the use of data in water programs with Shelley Wright. So thank you very much, and let's have Ken take control and bring up his presentation.
There we go.
Perfect.
All right, can you see the screen?
I can see the screen. Do you have a camera for us as well, so we can all meet you?
Oh, yes. On here. Hello.
There you are. Perfect.
See me? Okay.
Welcome, Ken. Ken Navidi holds a Bachelor's of Science degree in Natural Resources and a planning degree from Humboldt State University. He has worked for David Evans and Associates and Clark Regional Wastewater District in water resources. He has been a sales manager for Bainbridge Associates for 18 years, working with sales and instrumentation and controls for the water and wastewater industry. He enjoys discussing hydrology and how that affects flow monitoring. He has traveled extensively throughout Oregon, Washington, and Idaho to discuss monitoring water through plant processes and beyond. All right, Ken, take it away. Thank you.
Thank you. Well, I appreciate being asked to give a presentation at your conference. Generally, I do these live, so this is the first one that's actually a virtual presentation for me, so hopefully it goes well. I like to see a lot of faces out in the crowd, and that way I know that I'm not putting people to sleep. So this will be a different way of doing the presentation. And so we'll go ahead and get started. This is basically, I do a lot of flow metering discussions. I'm really narrowing this down right now to just monitoring and focusing on industrial wastewater. So industrial wastewater would be, wastewater coming from your industrial significant users, plants and such. So go ahead and get started here. So the next page here. So the history basically of flow monitoring all starts back in '72 with the NPDS, and where we started the NPDS permit. Basically, you know, it all goes back to the EPA and regulating, you know, discharges to the nation's waters. Um, in 1977, the Congress amended the Clean Water Act to enhance that NPDS program and controlling, shifted the focus from controlling conventional pollutants to controlling toxic discharges. So, so we all got involved and we all started, you know, monitoring and taking a look at industrial facilities and discharges. So that was the federal law, and then we now have local agencies. That would be the states and cities that are monitoring discharges. So, you know, Washington recently in July 2019, Washington State started a winery general permit. And in some of those permits, there were some flow monitoring requirements, depending on size and where they were discharging to. So there's those permits, and then as well as the city of Portland, BES has its own industrial wastewater permit and baseline monitoring. So with this, we got to consider monitoring. You know, what are we considering monitor? What do we have to consider when we're monitoring wastewater? Basically, if we're the facilities, we need to look at who the decision makers are and how do I comply with my permit, right? What does my industrial discharge permit say about monitoring? And on-site treatment, do we have on-site treatment at my facility? You know, and am I working with Department of Ecology or DEQ, depending on your state? And there's generally regulations that and requirements for their discharge permits that they have to follow. And also they're looking at, you know, water reclaim and water reuse programs now and putting those into effect at many industrial facilities. And then you're looking at as well off-site treatment and collection systems. So that's where many of the pre-treatment coordinators come involved. So why do we track industrial wastewater? There's several different reasons. Most of the time, it's for the purposes of reporting to your local municipality, state, or federal government, for my billing and compliance. So many industrial facilities, rather than water in, they would like to be billed to monitor flow out. Incidentally, a lot of times this helps to identify side sewer infiltration and inflow. It also allows them to monitor for reuse, water reuse. And then another requirement a lot of times is doing flow pace sampling rather than a time-based sample. So we'll have it involve a flow meter that will trigger the sampler. What should an industrial wastewater meter spec include? So first of all, a lot of times when I go to customers' facilities in the industrial side, I ask them, well, what is the requirement for the flow meter? And many times the answer is, well, I was told I have to have a flow meter. And so I said, well, you know, there's a lot of different, you know, different styles of flow meters, and depending on what your requirements are, we'd like to nail that down and get you the best, you know, the best flow meter for that environment. So a lot of times the spec will be a flow meter, and in the end of it, after a few years of working with industrial clients throughout that city, the city will start narrowing it down and saying, okay, well now, you know, we have to identify what the purpose of that meter is, right? We need to report, you know, we need to describe to the customer what the report is, right? Is it daily, monthly, or a yearly report? We want to see this on the report, right? So it's got to be in paper, or is it going to be a wireless transmittal of their reports, or is it cloud-based? And then a lot of times there's differences in the billing units, so we need to give them that requirement. A lot of places are now looking at comparing the water in with the water out, and most of our water source meters are in 100 cubic feet is one billing unit, so they'll try to match that with the outfall meters. needs to monitor at every 100 cubic feet. What's the meter's specified accuracy? That's a big question, and believe it or not, many customers or many industrial clients don't really ask that question. It's just, I just need a meter and I'm not 100% certain what the accuracy is. Just give me the meter that's the most accurate. And then the big question they'll have is what is the requirement for your flow range? In other words, do you know what your facility puts out in minimum and maximum flows? And then we need to get you, or put a meter that is going to operate in that range, right? And so, if you're looking at a facility where they've got 2 faucets and the average faucet's running at 2 gallons per minute, we've got 4 gallons per minute. They're running 2 faucets, and if they've got an 8-inch mag meter that starts reading at 33 gallons a minute, you're obviously missing all of that flow. So depending on the range and what you specify as the range, you could be missing quite a bit of flows, right, in that low end. So we also need to identify who is responsible for maintaining the flow meter. Many times they'll install the meter and they'll expect, well, I don't have the confined space entry equipment at the facility because I'm just the maintenance manager. So I don't know if I'm supposed to be responsible or if I have to hire a contractor to do that. So that needs to be identified as well. Does the meter need to work with a automatic meter reading system or AMI system? So some of the cities have made those requirements to the industrial facilities. Look, you get a flow meter, but that flow meter needs to work with this AMI system so that we can do the report. So that needs to be spelled out as well when requesting an industrial facility to have a flow meter. What is the signal required for the flow pace sampling or for the AMI system? Typically, it's like a relay that activates every few, every 100 cubic feet, or at a specific volume, it activates the sampler. And then they want to address any adders. There certainly are quite a few different flow meters, sensors that we can add to the flow meters for like pH, conductivity, and temperature. So if those are options that they are looking at down the road, we need to identify those so we can focus on a flow meter that could operate under those ranges. So source water, when I talk about source water, I mean, it's hard for me to say clean water because sometimes people pulling from rivers and streams and it may not be treated, but it's a source water to their facility, right? So we've got two different really animals when you talk about flow meters to the facility. One is your source water meter, which is coming to the facility generally in a closed pipe. So it's not open to the environment. It's treated, right, and it comes to your facility all nice and clean and a closed application. So you're talking about generally full pipe flow meters. So the typical ways of tracking your source water, because it's a closed source, a full circular pipe, the ID of the pipe is generally known, and it's made by the manufacturer, the ID, and so the area is a fixed unit in the pipe, and the water is sourced by a public municipality or private well, right? So you've got two different arenas. The public municipality will generally provide that flow meter, or you'll be required to put it on that well, and that's to monitor your flow coming into your plant. The water line many times is sized for fire flow, and when you have to size a flow meter for fire flow, you're generally going to be running at the very low end of what the flow meters can run at. So we find that the fire flow requirement requires that flow meter read very high, say 3,300 gallons a minute, But you know, the flow meter's low end is at 330, and most of the time they're running at say 400 or 500. So when you size a flow meter for fire flow, you have to take into consideration that the normal flow is going to be on the low end, and it could provide some inaccuracies when you're running at a low velocity. And I'll go over that in some later slides. Typically, you know, they measure with a full pipe is a propeller meter or a mag meter. Alternative measurements for your source water would be like measuring pump run times on your pumps. So you're just taking your head versus flow, you know, your pump chart and knowing what it runs, what the typical run pump is. If it's a 50 gallons a minute pump and times it by the time, you can figure out a rough idea of your volume. And then also doing well drop downs. Now, your meter accuracy when it's a full pipe, because generally these meters are just reading velocity, right? So these meters run off the continuity equation, which is basically the rate of flow equals the average velocity over the flow area. Well, since the area is known, we really truly a full pipe flow meter, all we're doing is reading velocity. So it's just really one sensor, and as long as they're pinned down, they'll run it at a much better accuracy range of 0.5% to 2%. So the most popular types of source water, again, is a turbine propeller meter. So water strikes the rotor blades and they rotate at a proportion of the velocity, right? So the size range of these flow meters are 1 inch all the way up to 72 inches. Generally, your prop meters run at about a 2% as far as accuracy. These meters do need to be maintained over a period of time. You know, the gears and the propeller, well, the bearings in them will start to get gunked up and they need to be rebuilt. Most of the time we'll find out when the flow meter just starts reading inaccurately and we get a call from somebody saying, hey, this meter's not running right. So we'll have to go out and we'll have to have that rebuilt. A lot of times you can just drop an assembly in. The assembly is this portion here, and where it's bolted in, and you can just pull that assembly out and put a new one in. These meters traditionally have been mechanical, so there's no digital display, but we do have digital displays now that can go onto these meters, and they're battery operated, and they will work with, say, an output signal to a SCADA or an AMI AMR system. So we're making these meters a little bit more smarter in that range. These meters also run at what we call a 10-to-1 turn down ratio. So if my meter runs at the low end at 30, so it starts reading and the impeller starts turning at 30 gallons a minute, the maximum it'll run would be 300. So that's what I mean by a 10-to-1 turn down ratio. The other types of meters that aren't as well known are orifice plates, V-cones, differential pressure. I call these differential pressure flow meters. And these are flow tubes that are manufactured, and you'll have an accurate ID dimension that's measured and a flange where it just bolts in. And there'll be a valve that's in here, 3-valve isolation manifold, and then it goes to what we call a differential pressure transmitter, DPI indicators. And the DPI indicators that are out on the market are Foxborough, E&H, and Rosemont make what a DPI, and it's able to read very accurately the pressure that's coming from the pressure that's built up from going around the cone segment. So we have a high pressure port here and a low pressure. The low pressure port is reading the pressure after the cone. The high pressure is reading before it. And so what this meter allows you to do is to put this in an area that's right off of a pump or right off of what we call a flow disturber. And so when you have flow disturbances, something that conditions the flow is always best. So the prop meters have what we call flow straighteners to try to straighten out the flow and condition it. And this meter has its own cone section that straightens out the flow. And so we could put this in areas where other meters it fail, right? The size ranges are from like 1 to 2 inches. This again is a 0.5% accuracy. And generally, again, the turn down ratio or the range is limited. It's about a 10-to-1 turn down ratio as well. Okay, next type of full pipe meters is a insertion meter. So we've got a mag insertion meter, which has a probe that goes down into the pipe. This one does not with an area, right? It's going to use the area of the existing pipe. So when customers come and purchase an insertion meter, the number one mistake people make is not being able to identify the ID accurately. So we have devices that can go down into the pipe and measure the ID for the customer. So they need to know what the ID of that pipe is. And we're just essentially measuring it with an electromagnetic velocity sensor with coils that are spaced out evenly along the flow pattern here. You can see these are made very, very large in size. And the good part is that they're very, very light. They're easy to install. And they also have a very good turn down ratio. It's a 40-to-1. So the range of this flow meter is 4 times the range of a typical prop meter. So this screen shows our typical mag meter, and these are probably the most popular meter now in the industry. You've got a fixed ID, you've got flanges, the coil, the magnetic coil is around the pipe, and it's measuring the velocity via electromagnetic velocity sensor. So the way that those work is that the coil creates a magnetic field, and as water passes through a conductor, it produces a small amount of voltage or current that the electrodes read. So it's directly proportional. The velocity is directly proportional to the current that's built up by the water moving through the conductor. And I have seen these in facilities at Wastewater that are operating under the minimum requirements of 33 gallons a minute. And so you definitely want to look at the minimum ranges of mag meters. Here it shows the meter accuracy is really good until you get to about 0.2 feet per second. At 0.2 feet per second, the accuracy just falls way off. So rather than source waters, we're now going to talk about process water. That's water that's coming out of the facility, right? Why do we monitor the process water? For recycling, reuse, for billing, again, reporting to the state, reporting to the municipality, and then flow-based sampling versus time-based sampling. And when I mean that's if you have like an auto sampler that you take out to a facility and you want to take some grab samples in that in the facility using our automated samplers, you'll put them out there, and typically most customers now are just putting them on time. Well, that basically weights each sample equally over a 24-hour period. And many times the facility is shut down. They may have just done a cleaning at the end of the night and thrown a bunch of soap down through the system where it's just sitting in the pipe, and that's where your sampler is grabbing from. And so find it to be much more accurate if we can do a flow-based sample rather than a time-based sample. So essentially the flow meter will trigger the sampler every 100 gallons or 1,000 gallons, whatever you've got that for an accurate grab sample to give you So keeping track of the process water outfall. The difference really with a flow meter coming out of the facility is a completely different animal, and I try to explain it that now we have partial pipes, right? We have an open source to the waste liquid. The flow is dependent on the pipe having a downward slope, right? So in other words, if we don't have enough slope, we're going to have a high liquid depth with very low velocities, and low velocities are difficult for flow meters. Generally, we're talking about a non-pressurized gravity outfall, and we have variable flow rates, we have variable levels, and variable velocities. So the area continuously changes depending on how much liquid depth you have in your pipe. Meters now don't have to measure just velocity, but they also have to measure the level inside, right? And generally, you want to have some way of having a way of calibrating the instrument on site. So it's the last part of it is able to calibrate on site is for open channel flow meters is much easier. When you've got a full pipe flow meter, there really is no way of really doing a wet calibration flow meter because you have no way of getting to those flows other than trying to do stuff. So they've got a test on the system. These and I'll go through them. They're transit time ultrasonic flow meters that you can put on a pipe, and those are at about 2% accuracies, and those are able to. But those are just testing it with a second calibrate. Some full pipe, second meter coming in. If you like a mag meter and it needs to be wet calibrated, it has to go back to the factory, right? So they have to take the flow meter out, send it back to the factory, get it calibrated, and have it come back. So many times they'll have a spare meter when that meter is going back calibration. This just kind of gives you an idea of gravity flow. Believe it or not, I've shown up at many different industrial facilities, and they have the first area, which is no slope. And so the liquid's backed up, you've got low velocities, and a lot of times they'll have debris and silt and very little drainage on a line. This can wreak havoc on your open channel flow meters. You typically want to have at least a 2.5% to 4% fall through the manhole and line so that it'll take solids with the liquids. If you've got it too steep, a lot of times you've got a very high velocity, the very low liquid depth, and many of our flow meters that are sensors that sit down in the bottom of the pipe, they'll have what we call rooster tailing. So the water comes at the sensor at such a high velocity, it just launches itself up over the top of that sensor. Also, when you've got too much fall, you're basically burning elevation. So in a design for a side sewer outfall, if you've got trunk lines and that type of stuff, you're burning up, your elevation. So you don't want to have a line that's running in an area. So the types of process flow meters, the oldest ones are our flumes and weirs. In 1970 with the Clean Water Act, basically we came up with submersible area velocity flow meters. We also have some process wastewater flow meters that are pumped where they're using some sort of a mag meter, and then we've got non-contact flow meters that sit up above the flow. I'll go through these here for you. So the oldest style of monitoring flow is your flume and weir, and basically flume and weir uses what we call a primary device, which is it is a primary device where it's calibrated and there's a restriction placed in that open channel that has a known head to flow relationship, right? And in other words, the primary device is proportional to the head and the level of flow that's in there. So the methods to obtain level in your primary device have traditionally been rulers, floats, bubblers, differential pressure sensors, and ultrasonic sensors. So on these, on the flume and weirs, is you'll have on the flume you'll have a converging section, a throat section, divergent section. So as the flow comes through it, it basically converges into the throat and leaves. I have seen some facilities that the flume is actually put in backwards, and that makes it very difficult to calibrate, and it doesn't work very well in that situation. So when you see flumes and weirs, you want to make sure that they're put in the correct direction. You generally want to have a little bit of a higher velocity so that solids don't settle out in the throat section. These don't work very well when we have a surcharge. So if you have a large amount of flow that comes through, if they dump tanks periodically, this might not be the best style meter for that. They also have to maintain these meters. So this kind of shows you some of the flumes and weirs that we have out on the market. You generally, it'll come with a transmitter, and you'll have a sensor that it's mounted up over the top of the primary device, and it'll be measuring your liquid depth. So with all ultrasonics here, they all have what we call a dead band. So it's an area where the meter will not read, right? So you got to be aware of what the dead band is of that sensor. So want to make sure that you've got at least 6 to 12 inches of space from the bottom of that sensor down to where it reads, right? So this sensor here has a 12-inch dead band. So, and then on your V-notch mirrors, you want to make sure that you know the notch angle, that you've got, your crest height and these dimensions, and these are plugged into the controller. So as it reads level, it understands and correlates that to flow. So for types of flow meters, what we've seen in the market is full pipe mag meters used on effluent lines. So the biggest limitations to this is, of course, it's only measuring velocity, so you got to make sure that your pipe is always full. So you want to make sure that you have good straight runs coming into your mag meters. And you want to make sure that they're always clean, right? That there's not a lot of debris that gets stuck in here. So I have seen this type of model where, say, the liquid depth is half here, it drops down into a P-trap to create a full pipe, and then it comes back out into a gravity situation. This type of situation does not work very well. I would not recommend using a P-trap style system, and especially if you have a facility and there's a possibility of plugging and that type of stuff, it could just make it very difficult for them to maintain. Also, I would not recommend using mag meters in a horizontal, because of course you have, you've got a partially full pipe on a typical horizontal gravity line. I would not recommend that as well. You could do it on inclines. You just want to make sure that there's some sort of a valve or check valve here that keeps this pipe full. All flow meters, most mag flow meters will have some sort of a empty pipe detection alarm, and it'll wreak havoc on the system when that sensor is just sitting in air. So the oldest type of flow meters is what we call our submersible area velocity sensors, and they're reading velocity either with a electromagnetic velocity sensor or a Doppler transducer that shoots a signal up through the flow and picks up a velocity, right? And so based upon the amount of pipe that it has, it's measuring level as well. So there'll be a level measurement is typically done by a pressure transducer, but there are also are what we call bubblers, and bubblers will will have an air tube that'll come down to the bottom of the pipe, and it pushes air out slowly out of that tube, and based upon the back pressure back to the controller, it's able to determine what the level of liquid is in your pipe. So with these sensors, these have to be maintained, of course, because you'll have sediment, silt, grease, solids, rags that'll generally come down and hit that sensor. These will work great in situations where you have large pipes with large volumes of water. These sensors generally are about 1 inch in height, and so it requires that you have at least 1 inch of flow to record velocity. Non-contact flow meters. So non-contact flow meters were designed basically with maintenance in mind. So they wanted to have a meter that would stay out of the flow, right? So this flow meter here uses radar for velocity and ultrasonic for depth. It's a very large flow range for this flow meter. We're talking upwards of a 120-inch diameter pipe all the way down to 4-inch. And they're easy enough to install and maintain. So this kind of shows basically a way of mounting that sensor to the wall over the crown of the pipe. It's just simply 2 bolts, and you mount this frame assembly to the wall. It measures, again, velocity with the radar horn and ultrasonic for level depth. You want to have it facing the flow so that the water is flowing this direction here and out. So as water is flowing across, it's shooting the velocity here at the invert of your pipe, and then you measure from the top of the pipe down to the surface of the water to calibrate this instrument. As the water comes up over the top of the sensor, it has a pressure sensor that's up in the unit housing itself that will monitor liquid depth above the top of the sensor. So the radar beam shoots downward and outward, and it reflects off particles, disturbances off the surface, causing a frequency shift. The return signals is compared to the frequency of the transmitted signal, and that's called the Doppler frequency, directly proportional to the velocity of the flow. With this type of flow meter, they've actually ran it through various different size pipes. So it also has what they call an logarithm for the velocity. So it's reading the surface velocity, but it's able to correlate an average velocity based upon tests that they've done at the factory. So how do we test flow through the factory? How do we test it in a closed pipe? I was talking briefly to you. This is really the only way of measuring flow in a full pipe that's active and at site. And that's by using what we call a saddle transit time ultrasonic sensor, or we have insertion meters. So it's just basically putting a valve and tapping into the line and putting a magnetic sensor down into the flow. And so these two types of flow meters could be used at various locations to basically verify that your flow meter, your full pipe flow meter, is working accurately. Limitations to these types of meters, of course, is, if you've got solids in there, they can foul with the transit time with ultrasonic sensors. If you've got concrete, steel type pipes, sometimes it has harder time traveling or sending a signal through that, as well as air. If you've got air in the line, it could affect you. But these are good low-cost ways of going out and trying to do verifications on your flow meters at the facility. So how do we do this in open channel? Well, we do this with portable velocity meters, and this one actually has level as well. So this is a flow meter that you can get from Hawk. It's a what we call FH950s. They're very popular for being used for stream monitoring with U.S. Fish and Wildlife Service, U.S. Forest Service, Army Corps of Engineers, and any type of large open channel system. This sensor is a great device to go out and to do what we call velocity profiling of streams and creeks. It's a point measurement. The accuracy of the electromagnetic velocity sensor in there is about 2%, and it just simply has a little thumb nut here, and we can mount this onto a pole, and we can have what we call it's called a staffing gauge. It'll have 1-inch increments or 1 meter increments on that staff gauge to give you depth, and you just move it up and down through the channel to do a pipe profile. So what is a pipe profile? It's going in and it's grabbing various velocities through your pipe, right? And it's determining what the average velocity is in the flow. And so with our profile methods, we have what's called a 0.9 Vmax and a 0.2, 0.4, 0.8. So the 0.9, it's basically I'll take the probe, I'll stick it down in the flow, I'll try to find the highest velocity, and I'll just times it by 0.9 to give me my average. This has been generally pretty close to an average. And then we can also do the 0.2, 0.4, 0.8, which is basically just taking it and bringing it up a quarter of the way, half of the way, 3/4 of the way, and then figuring out what my average velocity is in there, right? Because you got your pipe roughness coefficients here, you got different solids, that type of stuff. Or if the pipe's turning, you might have different velocities depending on where you're at in the pipe. So once we determine what my average velocity is and my floatar is reading the surface velocity, I'm then able to make a determination, hey, my average flow is X amount of my surface velocity, right? And so we're able to make adjustments in the software. The points to consider when selecting the flow meter: what is the quality of the water? Of course, is it clean? Is it dirty? Do you have a lot? I try to ask the customers a lot, what type of stuff do we have coming down here? Are there glue, laminates, sediments, grease, solids? What type of solids? And we try to make a determination of which meters would work best for that quality of the water. Does my source water have iron or manganese? Reason we ask that question is because a lot of your mag meters have a hard time with high iron and manganese contents, and those will require cleaning a little bit more. And does my meter read my expected flow range? So, we ask what's the lowest and what's the highest expected flow range, so we can pick a flow meter that will fall within that range. Can I shut down service to install or calibrate the flow meter? And so reason I ask that question is because obviously, if I'm going to put in a flume or a weir in a monitoring manhole, we're going to have to take that flow and do something with it when they go to install the flume or weir, right? And so they are going to have to take it out of service or find a route around for the flow. If I'm using my floatar sensor, what we do a lot of times is we find a place where they want to monitor the flow and put in a monitoring manhole. So they'll excavate down to the pipe, they'll cut a window over the top of the pipe. They then will put a cone section over the top of the pipe, and then they'll pour concrete as a base, right, and slope it towards the cut. So you can install, basically they call that kind of a pour in place base for the manhole, and they can install those while keeping the line in service. And it keeps the flow basically in the pipe, and you don't have any difference in roughness when it goes from pipe to manhole channel back into a pipe, right? So it keeps that pipe that same roughness coefficient through the monitoring process. What's the preferred location? What's the approach or site conditions? And again, I always ask full pipe versus open channel, right? So the only way for them to get a good full pipe out of a facility is to drop it down, drop their plant effluent into a tank and have it pumped out. And then what's my budget for purchasing and maintenance? And of course, you know, higher cost you spend up front on flow meters usually is less than maintenance. So some case studies. Where we installed some industrial flow meters. Well, one of them was Chateau Ste. Michelle Wineries. This was ahead of the winery permit. They wanted to do a pilot study on some of their facilities that were going to lagoons. So they picked 3 of their wineries, and we installed floatars in some cabinets here with a battery-operated cellular modem logger. And that logger sits up in the cabinet, and it's powered by solar. So this is completely an autonomous system. Doesn't require any power. You can put this meter pretty much anywhere, and it'll work. This sensor is actually sitting over the top of a open cut pipe. So they basically took the data and reported it over to DOE I think on a monthly report, and actually they're able to capture their reports online and give it to the DOE, and then they ask us to come in once a year and calibrate the flow meter with our portable FH950 and ultrasonic. Oregon Military Museum. This is another industrial facility we were asked to come take a look at. They actually had an ultrasonic flow meter on a flume, and the flume was backing up due to quite a bit of infiltration and inflow. So when they had storms, their meter was basically out of service. So we helped them by running a pilot study with Clackamas West. We were able to put a floatar in the situation downstream of that flume to prove that the flow meter worked. And at that point, the facility took out the flume and put our floatar at that location, and they were able to identify areas of I&I and reduce the facility. I think their flows are about half of what they were several years ago. So they were able to reduce their I&I quite a bit by having that flow meter out there. Monthly reports are basically downloaded and sent to Clackamas West, and they are billed off of this flow meter. Veilbreaker Brewery, this one's been in for about a year or so. It's Moxie. It's monitoring the plant effluent, and they wanted to take into consideration that they, you know, of course, a lot of their source water goes out in beer or evaporation. Therefore, they wanted to use effluent for measuring flow coming out and being billed. The challenge of this site, of course, was that it had a very flat line in there, so velocity is a challenge. It runs at about 1/4 to 1/2 foot per second many of the time, so you got to keep the line as clean as it can be, as well as trying to modulate their flow out so that they can get some good velocities to carry some of the solids. Again, this one's a wireless battery operated, and it sits down in the manhole. It just hangs in the manhole. John I. Haas out in Yakima, we've had this one out there for about 10 years. The city comes out and just basically reads the screen off the front here. We do run this at every 100 cubic feet, so it'll match their water. The challenge that we had with this flow meter is that they wanted to make it work with an AMI system, and so the Badger system that they had would take readings from a contact closure, or a relay. So we have the meter at every 100 cubic feet that it sees on total flow. It activates a relay, which then sends a signal to the Badger unit, and sends that to the city so that they can grab their flow meters without having to go to the meter. The data. Yep. Blue Ribbon Linen Supply. We've worked with these guys for probably over 15 years. They had a open vault where they actually had a flume and weir at one point here in this vault. They were able to take the flume and weir out and modify it to where it's just an open pipe channel here. Of course, you know, they get a lot of storm runoff and that type of stuff that sits down here in the sides, where we were talking about filling that back up with concrete so that they don't have the stagnant water. But that is pretty much the stagnant water that sits around the side there, and so it reads velocity and level in that pipe. It's a 120 volt AC unit. It also has a contact closure that activates their sampler. So when the city comes out, they plug into the flow meter, and it helps give them a flow pace sample. They basically just plug into it, and they take a monthly report, which they download from the instrument, and they hand it over to the city. This is kind of what we have for our summary reports. So, you know, most flow meters out there will have some sort of software, or you can go online and you can pick this report out. It gives them a maximum gallons per minute that it saw for the month, the minimum that it saw for the month, the average flow rate, and your monthly totals, right? And then for each day, it'll give them a maximum and minimum flow rate time, average, and totals for each day. So these reports are really what they'll submit to either the city, DOE, DOQ, whoever the person is that's asking for that flow data. So points to consider in summary of flow monitoring. You know, water sources in the Northwest are finite. Conservation measures are essential for industry growth. The industry should commit to reducing their wastewater monitoring plant outfall, and flow meters are a part of that. We want to place value on collecting data on the wastewater flow rates and chemical makeup of that waste. Industrial facilities can be a big contributor to the city's I&I problem. So micro monitoring industrial facilities may help in reducing some of that. We want to develop and implement a plan for specifying wastewater meters when the industry needs one. And one big question to think about is, how do we store the flow data we collect from industries, and what do we do with it, right? So, I mean, we're getting all this data from these industries. We're doing billing, but are we doing any other types of analysis? And how do we store all this information? So again, we work with quite a few different industries. We work with prisons, hospitals, pulp and paper, food processors, power plants, laundry facilities, and military bases. So many different facilities that we work with, and work on attaining flow. So I've got about, I think, 7 minutes here, so I figured I'd open it up to any questions.
Great, thank you, Ken. I appreciate you going through that all today, and the variety of all those meters. Learned so much. Questions. Not a lot have come in, but that doesn't mean they won't arrive in just a few moments as folks circle back on that part of it. But one question that was received is, so in the our permits that we write for our industries, it talks about having there's some language in there regarding 10% deviation for flow monitoring, and there with a mag meter, how do people calibrate those? Can you elaborate on that portion of it?
So on a closed pipe, and it's a mag meter that like a full bore mag. The way that they calibrate it mostly right now is they'll have a third party come out and do the verification on the flow meter. So they'll come out and put that transit time ultrasonic, that saddle it and compare it to that meter. and then they'll write up a report on the accuracy. So they'll calibrate it to that type of an instrument. We'll also have the insertion mag style meters that they can put into the pipe, and you can actually do a velocity profile with an insertion mag, which is basically picking up the velocities in the different pipe zones and then determining what the average flow. The real issue and problem with this is when you go out and you do kind of a calibration, you're running it at that one flow range. So as flows increase, your flow profile can change. So you can get much higher velocities along the wall at a lower, at a lower flow volume. But when the volume increases, then all of a sudden you get higher, you get slower velocities maybe in the center. So it can change, right? So when they go out, it's critical that the facility be able to hold their plant effluent or their water at a continuous rate, at a continuous flow rate, right? So that they can take the instrument and match it to that rate. So there's that, and there's another way that some of the meter manufacturers have in mag meters, and those are the coils. And so they'll go out, they'll test the coil, and they can make adjustments to the coil. It's what we call they call it a dry calibration, but essentially all they're doing is they're checking the coil for drift, and they're basically setting that coil back to where it was at when it came from the factory. So it's not a wet calibration. A wet calibration, it would be putting this mag meter on a tank, a volumetric tank, and running it through a flow facility. There are several places where you can have that done. Some of the meter manufacturers, like Micrometer, has a flow tank. So if you send the meter back to them, they'll calibrate it. There's also, I think it's Utah State has a flow facility, and they'll calibrate their meters. And then some cities actually have calibration facilities, like the city of Portland has their own, and they run it through their own calibrator. And so that's kind of the way that people do it.
Great, thank you. One other question. For batch discharge facilities, what of the meters you went through would you recommend? What type?
For batch discharge facilities, so that would basically be a facility where it's taking the flow and it's going into a tank, and you're able to discharge it at different times, right? So
Correct,
that
and
would,
it's not
yeah,
consistently
not
flowing all the time, theoretically.
right. Right, and so so if there's a tank and it's pumped, then a mag meter is a great way of doing it. I mean, you just put a mag meter on the line and it's pumped out, and you've got enough velocity when you're pumping it out, then a mag meter works great for that facility. If they don't have if they don't have a way of pressurizing that line on that batch discharge, and they'll go and they'll discharge, it really depends on their time of discharge. If it's less than a minute, then you want to have a meter that's reading continuous, right? So some of these flow meters are set to read once a minute, once every 5 minutes, once every 15 minutes. But if you have a batch and that batch doesn't run for a longer duration than 1 minute, then you want to have a meter that's live. And traditionally, those would be like your ultrasonic sensors that are on continuous power, and like over a flume or a weir. That probably would work best on a batch situation.
Great, perfect. Thank you very much. All right, that is all the questions that we received. Oh, there's one more at the last minute. Many of our industries have inline full bore mag meters for process wastewater. They do a heartbeat verification to calibrate annually. Do they need to remove the meter for external calibration? If yes, how frequently? And then uninstalling the meter may be difficult since there is nowhere to divert the flow.
Yeah. I mean, if they have to uninstall, they'd have to have a second meter sitting next to it and put it in. If they're doing an inline full bore heartbeat, generally that would be the test of the coil, and many of the meter manufacturers like ENH, Siemens, and even Micrometer now has a way of testing the coils. That's about the best that you can do in that situation. The only other way really of trying to calibrate um, your system is to try to lock it down if you can, and you knew that it was completely locked down, and you could run a couple faucets at a specific flow rate and do a flow rate calculation on those faucets, and then dump them into the system, and then figure out if it matches that. That's about the only other way I could think of doing that. Or putting in the transit time ultrasonic is a good way of doing it. If it's full pipe, um, you could use a transit time ultrasonic and get pretty close to within 2% accuracy of that flow.
Great. And does an annual basis for that seem logical?
It does.
Okay, perfect.
It does. And I know there's many facilities that do that with the full bore mags. They'll have somebody come in on an annual basis, and they're either doing one of two things. They're either putting on a transit time ultrasonic and strapping it on the pipe and comparing their flow rates on that meter device with the unit with the flow meter, or they're they're either doing it that way, putting the ultrasonic on there, or they're adjusting the coil. Right, they're going in and testing the coil on the device and making adjustments that way.
Great. Perfect. Well, thank you very much, Ken. We appreciated your presentation this morning and the time you gave us. Other Ken, do you want to put up the poll?
I will do that right now. Let's launch into it. Which of the following is a type of source water meter? Please select one. Turbine and propeller flow meter, V-cone or orifice plate meter, full pipe insertion mag meter, or all of the above. So all the CEU folks have at it. I'll give you about 30 more seconds. So about 5, 4, 3, 2, 1. I'm going to go ahead and close the poll and share the results. So 80% of you, all the above, which not that that's important for the CEUs, but that is the correct answer. So thanks very much. I'm going to hide that and pass the screen back to you, Carissa. Are you muted?
There we are. Do you see the agenda again?
Yes.
Perfect. All right. So next up will be David Knight, but I don't want to miss our 5-minute break. So let's come back at 10:08 and we will kick it off. Thank you.
Okay, welcome back, everyone. It is 10:08. The good thing about the digital age is that Krista's clock and my clock appear to be perfectly synced. So we're going to go to our next speaker now, David Knight. We'll be talking about local limits submittal package guidance. David's both majored and minored in engineering at Washington State University. So I don't think you have to go very far out on a limb to say David likes engineering. Uh, he recently spent almost 30 years with the Washington State Department of Ecology, and prior to that spent 10 years active with the U.S. Army Corps of Engineers, followed by almost 17 years of reserve duty. So David's family includes 5 sons, and when free time allows, he loves snorkeling near his home on Cebu Island in the Philippines. Dave, thanks for joining us today. I am handing control of the screen to you.
Dave, I believe you're on mute.
Unmuted. Okay, I'm gonna show my slides. Let me know if you can see the slideshow here. Is that coming up?
Yeah, you want to switch it.
Okay, will do. How is that working?
Perfect. All yours, sir.
All right. So I just wanted to say to start with, I'm so honored to be able to talk to you. I've worked for the Department of Ecology 29 years. Recently, I've transitioned out, and now if you want to get a hold of me, you'll have to use my email address down at the bottom here, or my phone number there, to send me a text or phone message. I'm going to talk to you about something that you don't hear a lot about. It's the documentation that you need to establish that your local limits are technically based. And I thought that this would be a great topic to talk about this year, because it's not a topic that you think about a lot until you get to the point where you're doing local limits, or you're hiring someone to do them, and you need to know what kind of documentation do you need. And I found that it's really hard to find out exactly what that is. So I thought this might be a good presentation to help everybody figure out what that documentation should be, so that you can do a really good job of either doing those submittal package yourself, or having someone do it, and you're going to be able to see if they've done a good job, because you know what it's supposed to have in it. So I'm going to cover a little bit of background, the role of local limits, and the process, and the types of local limits. And then mostly I'm going to talk about submitting the technical basis. After that, I'll talk about what follows after that a little bit, and I'll give you some resources and references, because I think those are really helpful, especially when you go back. And hopefully this will be a presentation that you'll be able to save, and you'll go back to when you need to do local limits, and you can refer to this later. There's a lot of regulatory drivers for this whole process. 403.5 is this citation that talks about the general and specific prohibitions in 403.5 A and B. But when you get down to 403.5 C, you'll find that it requires POTWs both with pretreatment programs and without pretreatment programs to develop local limits to protect themselves. And so if you have a POTW and you don't have a pretreatment program, and you think, well, I don't need local limits, that's not exactly true. You look at 403.5 C2, and it says that all other POTWs, the ones even without pretreatment programs, shall develop and enforce limits to address pastoral interference and ensure that they can comply with their permit. And added with the streamlining was also provision that POTWs can use best management practice in lieu of numerical limits. That was the streamlining provision, and they could already use them in addition to numerical limits. And I hope that you'll think of that when the time comes. And then when you get down to developing a program at 403.9, it talks about the limits must be technically based, legally sufficient, and approved by your approval authority. And users have to be notified, the public involvement has to be done, and the authority to implement these local limits codified. So that really gives you a full list of the things that are the key areas of this submittal package that it has to touch on. And if you're revising your local limits, you'll need to look at 403.18, the procedures for modifying programs. States are obliged to help you in this process, but you need to ask them for that. When it comes to defending your local limits, if someone ever questions whether your local limits are really adequate and thinks that they shouldn't have to abide by those and takes you to court, it's not going to be the states, however, or your consultant that is there defending you. You're going to have to be able to say why you believe these local limits are technically based. And so your public works director is going to be looking to you to say, hey, you know, defend these for me. And so you and your legal support staff will be doing that. And if you're just looking at your NPDES permit application, it also requires a written technical evaluation of the need to revise limits. And this is typically asked for every year if you have a delegated program. But if you don't, then it would be done with your NPDES permit application. So let's talk about some practical reasons for the local limits. I think we all know that local limits protect you, but I wanted to say that it's important to do local limits to be proactive. The general EPA methodology bases the need for local limits on whether you're pretty close to your capacity or not. I think that there's a big drawback in that is that, you know, you're gonna allow something to come into the plant before you know that you can take it, and that's, you know, problematic. Local